Right. Let us now move on to the next problem. It's problem number 26. Now this is another quantum mechanical problem. It says the linear operator O cap acts on two orthonormal states of a system. There are two orthonormal states, psi 1, psi 2. They are orthonormal. They are orthonormal, which should mean psi 1 star psi 2 dx. Psi 1 star psi 2 dx should be 0, and psi 1 star psi 1 dx equals to psi 2 star psi 2 dx equals 1. This is what orthonormal state means. And operator O cap, when it acts on psi 1, gives you psi 2. When it acts on psi 2, it gives you a superposition of psi 1 and psi 2. And the state of the system is already in a superposed state, which is given by square root of 2 psi 1 plus I of psi 2. So there is a phase factor of pi by 2 e raised to minus I pi by 2, and that comes here as I. This is the superposed state system. And we are asked to find the expectation value of O in psi. We have to find the expectation value of O in psi. Let's see how we can go about doing it. So first of all, let us start with the expectation value expression, and that is simple. The integrals here are plus infinity minus infinity plus infinity minus infinity. And the same goes here. And the psi star O cap sa psi dx. O cap dx. This is how it goes on. And now we have to expand it out. We simply have to expand it out and see what we get. So psi star, and we take the stars, we cannot forget it. And remember, I, the complex conjugate of I is minus of I. It's a complex number. It's an imaginary number. Psi 2 star O cap psi 1 plus I of psi 2. Now this, after beyond this point, is just algebra. Beyond this point is nothing more than algebra. And first we let the operator O act on psi 1 and psi 2. We know that O psi 1 gives you psi 2, and O psi 2 gives you another factor of 1 by root 2 times psi 1 plus psi 2 of x. So it's half. That's half times integrals. Now we have to carry out some multiplications. And let's simplify this first. let's write it out. Psi 1 by root 2 plus I psi 2 by root 2 d of x. And now we'll just carry out the multiplications. So the first term is psi 1 star psi 2. And the second term is psi 1 I times psi 1 star times psi 1 star over root 2. The next term I psi 1 star psi 2 over root 2. The next term is multiplying psi 2 with psi 2 with psi 2 star with psi 2. And then you have I times I is minus 1, but it's minus already there, so it's plus. So psi 2 star psi 1 over root 2. And finally you have another plus sign, because I square is for minus 1, but there's a minus sign, which is psi 2 star psi 2 by root 2. All of this coming under dx. All of this comes under dx. Now we can rub out just a few lines. Keep the rest of them. Now it's straightforward. We apply the orthonormal condition on psi 1 and psi 2 in the complex conjugates. The first one comes out to be 0. The second one comes out to be 1. And so that is just I over root 2. The third one comes out to be 0 as well. Fourth one comes out to be 1, so it's minus I. Fifth one comes out to be 0. Sixth one comes out to be 1, so it's 1 over root 2. So that concludes our integral. And the integrals finally will look like I plus 1 over root 2 minus I. Or if you insist on taking out the root 2 outside the brackets, then it's I plus 1 minus I to 2. Or if you rearrange it, it comes out to be 1 over 2 root 2 1 minus I root 2 minus 1. And there is an option which is D. This is our option D. So that is our expectation value. That is our expectation value for the operator OCAP. So answer D. Answer is option D. That concludes our problem number 26. Let's move on to the next problem, problem number 27. What does it say? Consider a one-dimensional infinite potential well of width A. So, let us draw an infinite square potential well. It goes to infinity, and its width is about A. The system contains 5 non-interacting electrons. So there are 5 electrons which are not interacting. So let me write out a bit clearly. There are 5 electrons. This is how I used to do. This is what I used to denote an electron, and E with a minus sign over it. Electrons, and each of mass m, and the temperature is 0 Kelvin. There are no temperature effects. So what is the energy of the highest occupied state? First, we have to write down the energy formula for the infinite square? Well, which, if you remember, goes as n squared times pi squared over h cross squared by 2 times m over a squared. 2 times m over a squared. M is the mass of the particle, a is the width, n is simply the level number. N goes from 1 to 3 up to infinity, because it's infinite square. So it can go, it can keep going, keep going. Now there are 5 electrons. What is the highest state, highest occupied state, and what is the energy corresponding to it? So, in this case, if we consider that the electrons are non-interacting and the electrons, you know that the electrons satisfy Pauli exclusion principle. No 2 electrons can occupy the same state of quantum numbers. The electrons satisfy Pauli exclusion principle, which means 2 electrons cannot have all their quantum numbers same. Now here, we're not considering the spin of the electron. So ignore the spin, which basically means that each of the states can only be occupied by 1 electron. Therefore, the fifth state would be the highest occupied state. 1 electron per level. Highest state occupied. Highest occupied state is 5, and therefore it would be 5 squared times n squared pi squared h cross squared over 2m a squared, and that will give you a factor of 25. That's 25 times, I'm sorry, not n squared, because n is 5. I've already put 5 here, so 2m a squared. That is our option A. That is our option A. So that should give us, so that is our highest occupied state, and the correct option here is A. And that concludes our problem. Let us move on now to the next problem.